Hello, welcome back to video 2 of the ratio test. We did the first example and we got an inconclusive test. So let's hope for number 2 that we get a better outcome. I'm looking at this setup. This setup looks familiar. You should recognize it as a P series. It's a P series where P is equal to 2 and that value is greater than 1. And so therefore I know it converges. So can I do the ratio test to determine whether or not it converges? By the way, as I return to number 1, I do want to point out I forgot to put the absolute values here. But in this case, we really didn't need the absolute values because n was approaching infinity and that was just going to positive numbers anyway. When I do this, I also want to point out that we're going to take the limit as n approaches infinity of, now remember, the n plus 1th term means wherever you see a variable, replace it with n plus 1. So that's n plus 1 squared, divided by the original nth term, which is 1 over n squared. And then I'm going to take the absolute value. However, I recognize that I am just plugging in numbers that are positive, and when I square here and here, it's just going to produce positive. So I really don't need, in this example, I really don't need the absolute values. So I'm going to take the limit as n approaches infinity. Let me fix this, quote unquote, fix this. Multiply the top and then the bottom by n squared, and I think you'll get this. Well, they're both going to grow. As I substitute big numbers, this is going to grow because it's squaring, and this is going to grow because it's squaring. As a matter of fact, since this is n squared plus 2n plus 1, they're going to grow at the same rate. So this again equals 1. That means the ratio test is inconclusive. Well, why would you do this to us? We've done 2 examples and the ratio test doesn't work. I want to show you that just because it doesn't work doesn't mean it diverges. Just because it doesn't work doesn't mean that it converges. We really don't know. So we have to rely on other things that we've studied, like a P series or a harmonic series, to figure out the convergence of that given series. So I will say that if we continue to do this with other P series, 1 over n to the third, 5 over n to the 10th, we're going to get inconclusive tests. So I guess we could write this. The ratio test does not work with P series. But if we know we're dealing with the P series, well, then we know how to tell whether it converges or diverges anyway, that I really don't need the ratio test, right? Okay, so then when does the ratio test become helpful? If we look at number 4, this might be an example. I'm going to take the limit of the absolute value of the n plus 1th term. The n plus 1th term means 4 to the n plus 1 over n plus 1 factorial, divided by the original nth term, which is 4 to the n over n factorial. And we're taking the absolute value of this. Well, now I have a fraction within a fraction, and that fraction includes exponentials and factorials. So let me see if I can make this look a little bit nicer. That would be the absolute value of this is going to stay the same. So the way I'm going to approach this is I'm going to take the numerator and multiply it by the reciprocal of the denominator. Now here's that setup we were talking about before. If I have an exponential whose exponents are being added, I could rewrite this as 4 to the n times 4 to the 1. Why would I do that? Because then I would be able to reduce this. And then I notice this is 4 to the 1, right? And then I notice I have factorials. So that's the same situation that we were talking about before, which is, let me take the limit as n approaches infinity. Let me try to make this a little bit nicer. 4 times n factorial divided by n plus 1 factorial. Now I'm left with that. That's a little bit easier to work with. Oh, well, the denominator is really n plus 1 times n factorial, because it's n plus 1 times n minus 1 times n minus 2 times n minus 3 times yada, 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 all the way down to 1. So this is really n factorial. And then I can reduce the factorials. So really, I'm just taking the limit as n approaches infinity of 4 divided by n plus 1. And if you take that limit, you should know that this equals 0. That is less than 1, so the series converges. Which series? The original series that I started with. That's how the ratio test works. So when should I use the ratio test? I should probably use the ratio test if I have factorials, for sure. I could also try to do the ratio test if I ever have exponentials. That could work. But this is how the ratio test works. Take the limit of the n plus 1th term divided by the nth term. If you get a limit value that's smaller than 1, less than 1, it's going to converge. If the limit value is greater than 1, it's going to diverge. If it's equal to 1, we don't know. It could converge, it could diverge. We just don't know. Got to try something else. Let's do number 3, and then we'll pause this video and see some more problems in the next one. All right, let's take the limit. So I'm using the ratio test. As n approaches infinity, of the n plus 1th term, wherever I see a variable, I'm going to replace it with n plus 1. Just like that. Taking the absolute value, by the way. And then I'm going to divide by the nth term. But I already noticed this is getting really complicated really fast. So instead of dividing by the nth term, I'm going to multiply by its reciprocal, which is 5 to the n over n squared times 3 to the n plus 1. And I'm closing the absolute value bar there. Now this looks really complicated, except watch what happens. N plus 1, I believe that's n plus 2. So I can just rewrite this as 3 to the n plus 2. Let's use the color that we used. 3 to the n plus 2. And because it's 3 to the n plus 2, that also means that I could rewrite this as 3 to the n times 3 to the second. I could also rewrite this 5 to the n plus 1 as 5 to the n times 5 to the 1. And I can definitely split this exponential up into 3 to the n times 3 to the 1. I'm multiplying all the way in the numerator. I'm multiplying all the way in the denominator. So if there's anything that appears in the numerator and denominator, those factors can be reduced. So I'm going to reduce 3 to the n and 3 to the n. I'm going to reduce 5 to the n and 5 to the n. I'm going to reduce one of these 3's with one of these 3's, and it's going to leave me with 3 to the 1. And I think that's everything. So what's left over? Well, we started with a lot of pieces in this puzzle, but now I'm left with n plus 1 squared times 3, because this is gone, 3 to the first, okay, divided by 5 times n squared. Close the absolute value. And now we're going to take the limit of this. Well, the numerator is growing, the denominator is growing, but because the biggest power on the top is n squared and the biggest power on the bottom is n squared, they're growing at the same rate. So therefore, this limit is just 3/5. And 3/5 is less than 1. So therefore, this series converges by the ratio test. We took the limit of the nth plus 1th term divided by the nth term. We simplified as much as we could, and we got an answer that is less than 1, so it converges. That's how the ratio test works. We'll come back in the last video here coming up, and we'll do a couple of more examples before moving on to the alternating series test.